Dynamic equilibrium. Up until now, we've talked about reactions going one direction. Turns out a lot of reactions can go forward and reverse, just like your car can go forward and reverse. So a reversible reaction can proceed both in the forward and the reverse reactions. And when we have the forward reaction rate equal to the reverse reaction rate, that's called dynamic equilibrium. Those reactions are occurring both in the forward and the reverse direction at the same rate. What happens is that the concentrations of reactants and products aren't going to be changing. So on the surface, it looks like nothing's happening. And yet you have forward reaction making product and reverse reaction making reactants. And the reactants and products are being depleted and formed at the same rate. So it's constant change, and yet it's the same. It's kind of a strange idea. One thing you might think about is a busy airport in the middle of the day. And if you counted the number of people in the airport every hour, it's probably going to be roughly the same number of people, right? Is it the same people in the airport all day long? Not unless something funny's happened, right? Because people are coming and people are leaving. But if they're coming and leaving at the same rate, it's at equilibrium. The number of people in the airport is the same, but it's not the same people. Okay, that's what's happening with a dynamic equilibrium. Here we're going to look again at this blue and white reaction. And here we have our little boxes, and now with a timer. At time 0, in this box we have 8 hydrogen molecules and 8 iodine molecules and no hydrogen iodide molecules. Okay, so we just have the reactants. And they're going to run into each other, and they're going to make product, and after 15 seconds, we've got 6 hydrogens and 6 iodines, and we have 4 hydrogen iodides, because for each hydrogen that reacts, we get 2 of these. What does that do to the rate of the reaction? If we have fewer reactant molecules, it causes it to slow down, right? And then we get to 30 seconds, and now we've got 4 hydrogens, 4 iodines, and 8 hydrogen iodides. This reaction goes in both directions. From here to here, we've increased the amount of product. If we look at the reverse reaction, what's going to happen to the rate of the reverse reaction as we get more and more HI? Higher concentration, higher reaction rate. And at this point, we have actually reached equilibrium, and as time goes on, the numbers of reactant and product molecules do not change. And yet, particles are colliding and forming new particles, and these guys can also run into each other and reform the reactants. And so both of these processes are going on. This is very important to realize. Equilibrium does not mean that the concentrations are equal. They could be equal, but most likely they are not. That depends on a lot of different factors, but it does not mean that they're equal. What it means is that they're being formed at equal rates. The forward reaction is equal to the reverse reaction. In your book, they have this nice analogy, population analogy. Imagine that Narnia and Middle-earth were neighboring kingdoms, right? And they're just separated by this river. And originally, Middle-earth is very underpopulated, and Narnia has gotten to be overpopulated. And now the border has opened up, and people are allowed to move between the two kingdoms, right? So it's very crowded over here. Naturally, people are going to move over to Middle-earth. There's free land available. There might be incentives from the government. Come farm, grow food for us. And so a lot of people start moving to Middle Earth. Is anyone moving from Middle Earth to Narnia? Not much, no. There's hardly anybody over there. As time goes on and more people move to Middle Earth starts getting a little bit crowded. And now some of the people that moved over here are thinking, you know, it's not so much better over here. I think I liked it where I was before. And so they start moving back. And you're going to have constantly people moving from here from Narnia to Middle Earth and from Middle Earth back to Narnia. What you'll find is, depending on how attractive Middle Earth is versus Narnia, one of those kingdoms may have a higher population than the other. But it's going to settle down and become pretty stable. Not the same people in each kingdom. There'll be people moving back and forth, but the same number of people. Does that make sense? It's dynamic equilibrium. Okay, now we're going to watch the video. I have to get back on the Wi-Fi, or the Wi-Fi, as my mother-in-law calls it. She's 80. What do you expect, right? It's amazing that she even knows it exists. I'm having trouble with my Wi-Fi. Let me try not to snicker. Come on, stop that.
Say two people are walking down the street and they bump into each other. They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if two people were to bump into each other, and during that collision, one person's arm got severed and reattached to the other person's face? Now that sounds really weird, but it's similar to one of the many ways that molecules can react with each other. Two molecules can join and become one. One can split apart and become two. Molecules can switch parts. All these changes are chemical reactions, and we can see them happening around us. For example, when fireworks explode, or iron rusts, or milk goes bad, or people are born, grow old, die, and then decompose. But chemical reactions don't just happen willy-nilly. Everything has to be right. First, the molecules have to hit each other in the right orientation. And second, they have to hit each other hard enough, in other words, with enough energy. Now, you're probably thinking that a reaction just happens in one direction and that's it. Sometimes that's true. For example, things can't unburn or unexplode. But most reactions can happen in both directions, forward and reverse. There's no reason that our face arm guy can't bump into armless girl, reattaching that arm back to its original socket. Now let's zoom out a bit. Now let's say that you've got 1,000 people on the street, and all of them start with their limbs normally attached. At the beginning, every collision is a chance for person A to transfer an arm to person B's face. And so at the beginning, more and more people end up with arms attached to their faces, or arms missing. But as the number of people with arm faces and missing arms grows, collisions between those people become more likely. And when they bump into each other, guess what? Normal appendage people are reproduced. Now the number of limb transfers per second forward will start high and then fall. And the number of limb transfers per second backward will start at 0 and then rise. Eventually they'll meet, they'll be the same. And when that happens, the number of people in each state stops changing, even though people are still bumping into each other and exchanging limbs. Now, how many people do you think there are in each state? Half and half, right? No. Well, maybe. It depends. It could be 50-50, but it could be 60-40 or 15-85 or anything. We chemists have to get our little gloved hands dirty. Well, we're in a lab, so not really dirty, to figure out what the actual distribution of molecules is. Even though each of these limb transfers is a pretty dramatic event for the people involved, if we zoom out, we see population numbers that don't change. We call this nirvana equilibrium, and it doesn't just happen with chemical reactions. Things like gene pools and highway traffic show the same pattern. It looks pretty still from 30,000 feet, but there is lots of crazy stuff happening on the ground. You just need to zoom in to see it.
Any questions? Does that help you kind of see what I was talking about? It's always fun when you're getting ready for lecture. It's like, oh, darn, I have to go mess around on YouTube. This is such a burden, right? The hard part is not getting distracted. Let's see if we can get these guys hooked up again. Reconnect. Yay!